So, to make some qualitative predictions about relative lattice energy, you have to understand that the attractiveness between 2 point charges, which is how we're modeling ions and ionic bonding, is proportionate to their charges. So, Q1 and Q2 are charges of the ions that are forming the ionic bond, and inversely proportionate to the distance between them, or the bond radius, if you like. Okay, or like atomic size. Okay, same kind of thing, right? So the reason for this is because electrostatic potential energy comes from Coulomb's law. So this is Coulomb's law with the constant taken out, basically. Okay, so the bigger the magnitude of charges, the greater the energy, attractive energy between them. Okay, and the closer together they are, the greater the attractive energy. Okay, so this is how we're modeling point charges. So if we're looking to compare two compounds, you've got to work out what is the same and what is different. Okay, so we've got magnesium and beryllium iodide. So they are both bonding to the same anion. Okay, so the charge on the anion is constant. Beryllium and magnesium are both in group 2. So Q1 is going to be the same for both of them, right? +2 and -1. So the magnitude of Q1 times Q2 is the same for magnesium iodide as it is for beryllium iodide. Therefore, this must be a size problem, okay? So make sure we haven't forgotten our trends in radius, etc. So we know that atomic radius is going to decrease going across a period because effective nuclear charge increases, so radius decreases. And then as we go down a group, we know that the radius is going to increase going down a group. So in this case, magnesium is bigger than beryllium, okay? Therefore, magnesium and iodine, those charges are further apart in magnesium iodide, so there's going to be less attractive energy. In beryllium iodide, they're going to be closer together because R is going to be smaller, the distance between them. Okay, so small thing on the bottom of a fraction means the thing that it equals is going to be bigger. Okay, so we would predict that beryllium iodide would be the biggest out of those two. Okay, so the reason is smaller R, which give bigger E, right? Okay, so then let's compare the others. So we got sodium sulfide and sodium oxide. So we've got the same cation each time now. Let's get rid of those so we don't get confused. So sodium is the cation, and we are asked the difference between oxide and sulfide. So again, the charge is the same. Q1 for the sodium is +1, Q2 for the oxygen, the sulfur is -2. So same charge magnitude. Again, it's going to be a radius thing. So out of oxygen and sulfur, sulfur is going to have a bigger radius. Oxygen will have the smaller radius. So the sodium and the oxygen will be closer together. So you'll have the bigger energy for the sodium oxide. All right, so what's the third combination then? Let's have a look. Barium fluoride versus barium oxide. So again, we've got the same metal, barium, and then fluorine and oxygen. Okay, so this time they're not in the same group, but they are in the same period. So again, we've got the same charges. For the cation, barium is +2. So let's just say Q1 is the metal. Q1 is +2 for the barium fluoride. And for the barium oxide, Q2 equals +2. For the barium fluoride, Q1 is -1, okay? But not Q1, dearie me, Q2, and that's Q1. Talking and typing is a hard thing, right? And Q2 for the barium oxide, well, oxygen is -2. So the magnitude of the charges are greater for the barium oxide. Okay, so I'm not even going to look at radius, okay, because whenever you see an actual integer difference in charge, that is a much bigger effect than less than an integer difference in radius, okay, because remember these radiuses will be like in angstroms, 10 to the -10 meters, so like a difference of like 0.5 in the bond distance is negligible compared to a whole 1 ±1 in terms of charge. Okay, so I'm still ticking things here. Okay, so it's going to be bigger charge, so that will give us bigger energy for barium oxide. Okay, so remember the effects of charge is bigger than the effects of radius. So if you're not sure, if you see a difference in charge, Don't even bother looking at the radius. Charge is your answer.